Tilburg University and MindLabs present TAISIG Talks, the podcast that keeps you updated on the latest developments in the field of artificial intelligence in just 1 hour.
Welcome to the TAISIG Talks. TAISIG is the Tilburg Artificial Intelligence Special Interest Group of Tilburg University. My name is Pieter Spronck. I'm the chair of TAISIG. And the TAISIG Talks are meant to introduce some of the research that is done at Tilburg University in the area of artificial intelligence. So in general, we invite 1 or 2 guests from who do research in this area from Tilburg University. And today I'm talking to Bruno Nicenboim about computational modeling of complex behavior. Bruno, can you introduce yourself, please?
Yeah, sure. So, my focus of interest is mostly language comprehension, how people read and understand language. But I also worked a lot in methods, and I got interested in computational modeling and in how researchers can frame a problem in order to make it more precise and in a computational way, in order to answer also questions that are more interesting than null hypothesis testing, comparison between conditions, things like that.
Okay. Well, you already now said a little bit about what computational modeling is. Maybe we should talk a bit more about that. But the whole title is Computational Modeling of Complex Behavior. And what kind of behavior are you then talking about and what makes it complex? So can you just give us a general introduction to the topic of computational modeling of complex behavior?
Yeah. So by computational modeling, I refer to building some program, some algorithm that behaves in the same way that a human behaves or that an animal could be or a group of people. The idea is that we don't want to have a behavior which is optimal. We want to have a behavior that's realistic. And that behavior, which can be understanding a text or it could be how to make a negotiation, it's driven by theories. We implement these theories as a program, and then we run simulations. We try to feed them to the data. We see to what extent the data and the model coincide that can tell us something about the theory that is behind the computational model. And a bit this idea of complex behavior came because when you look at computational models mostly in cognitive psychology, in mathematical psychology, what you see is always models of very, very, very simplistic tasks. Choose between 2 options, which can be decide if a string of letters is a word or not a word, or it could be you have points moving to some direction, and you in random movement of dots, and you need to decide to which direction the dots are following, and then there is kind of a big disconnect between what most psycholinguists or cognitive psychologists or cognitive scientists care about and what is possible and easy to model. And yeah, a complex behavior would be something that goes beyond the very simplified task that you can do in a lab.
Okay. So I can understand that when you have a simple behavior, that you want to create a model of it, and a computational model, that's fairly easy to test, or relatively easy to test, whether it is a correct model, because it's a simple task, so you can just compare the outcome of the model with the task. And I can imagine that is a lot harder for a big, complex model, very complex behavior. So for complex behaviors. Now, what I have seen in practice, and actually it reminds me a bit of my own PhD thesis, where I also said, okay, you have these people working on very simple problems. I want to work on the very complex problem, and I'm gonna do stuff which I think might work, but I'm not even considering whether or not it's theoretically correct. I'm just interested in whether it works or not. But I think when you talk about computational modeling, you still want a theory behind it, right? So you have the complex task, but have a theoretical model. Am I correct here?
Yes, completely correct. The idea is to have models that are mostly theory-driven, because the idea is to understand how people behave, how people think, how people interact. And the understanding comes from theories. The problem with theories is that they are usually very vague. And even if you want to make them precise, you never know to what extent they are precise until you really implement them into a computational model and see what exactly these theories are saying. And that introduces also a lot of problems and complexity, because when we think about how people might behave, you have all this came because almost 2 years ago, I, with Ricardo Fusaroli and Marieke van Vugt, we did this Lawrence workshop on this same topic, and then we invited people to talk, to give ideas about what type of complex behaviors they were interested in, and people with more experience in modeling to try to bridge between these two groups: the modelers, who usually work on very simple tasks, and people who have more of a domain expertise, which work on more complicated phenomena. And I think that one of the funniest examples was how in Sydney there is a constant struggle between homeowners that have bins that are opened by cockatoos, and these cockatoos keep learning how to open the bins, and then you have, that's the problem. So that's the behavior of two groups: the attackers, which are these birds, and the defenders, who are the homeowners that want to defend their bins. And
so then, you talk about garbage bins, I assume?
Yes, garbage bins. Yeah, and so it's not, and the idea was to try to think about what is going on there, what are the mechanisms that lead to the cockatoos to learn and to behave in the way that they behave, and how also what leads to the behavior of homeowners. And what this group, for example, that end up doing is a simulation. So they also had data, but what they wanted to do is to abstract from the small details and try to understand what would happen if we increase the security of the trash bins. And then you see, according to the model, and it seems also according to reality, that the birds spread more quickly because they have travels there in the places where the bins are harder, and then they spread to other areas. And then the people who have, where the birds are no longer there, they also relax the security, and then the birds came back. And so you can also test things that are outside of what really happened, and simulate different scenarios to try to understand the possibilities. But this was all, that was all based, for example, in this case, on reinforcement learning.
Mm-hmm. Okay, well, so one of the things I want to talk about is why you would want to do this. Now, you now basically gave an example of why you would want to do this, namely, okay, you have a problem. The problem is that there's birds that open trash bins and take the trash out and make a lot of mess, and then people don't want that. They lock the bins, and then what was the consequence of that? And then probably you form a theory, but and then you can predict what the consequence would be, and then you, if that is correct, then you can anticipate future problems. And I can imagine that is very useful in many areas. But in principle, you start out with a situation where you have the current situation, and you form a theory, you build a model, you make the prediction. But if your model is not correct or not completely correct, then your prediction might be completely wrong. And I can imagine that for complex behavior, that it's very hard to have a good theory that actually explains everything that is going on. So it's not directly a question, but can you respond to that?
Yes. Definitely your theory won't be exactly right. And the idea is to have an abstraction that can capture the main patterns and can tell us something, both to be able to make good predictions, but in some cases it's also about trying to understand what are the underlying mechanisms that lead to that behavior. So it's not the case that always computational models have great predictions. Sometimes the predictions are not that great, but you still can see. So in my own area, in language comprehension, I don't think the models are that great in terms of predictions. We have completely theory-driven models like large language models that are much, much better in predicting what is the next word, for example. But we cannot really understand how people understand language, how people read. We cannot understand what leads to difficulties in reading from just inspecting a large language model, because we don't have, it wasn't created with theory in mind. But if one creates a computational model that's grounded in theory, then you can investigate to what extent it reflects the patterns that you see in the data. You can make new predictions and then also test them. You can create a new experiment where these new conditions that the simulation is telling you that they might happen, and then you test that with human participants reading a text, and then you can see if your theory, if there was a problem with your theory, and then you have an opportunity to go and fix, to learn something about the theory, to understand what was wrong, to be able to fix it, to understand the limitations, to decide if you need to throw away that theory and it's completely incorrect, or if there is still room for improvement. And so I don't think that theory-driven models will be as good making predictions as data-driven models, but the idea is more understanding than really capturing all the small details of the data that we see in the world.
Okay. Yeah. I'm thinking a bit about, I'm thinking about other sciences like economics and psychology, for instance, where there is a lot of theory. So, maybe not theory, but ideas of, I think that people do X because of Y. And then you can set up an experiment and test that out. The extra step that you're now talking about is capturing this theory in a model, in a computational model, and use that for making the prediction. So what is this then, and I think I have an idea of the answer, but what is this adding to the whole process?
So I think it's fair to call them theories, even if they are statements, because people in economy and psychology treat them as theories. So those ideas about behavior, of what leads to what, they are usually causal, they are implying an explanation. The issue is that they are very, very vague and determined, and then they can predict the difference between two conditions, but there are so many other ways to have a difference between two conditions beside that theory, and that theory might have implications for other things, but it's never very well specified. And then creating a computational model forces you to think about all the small details and all the details of the theory that are unsaid, and to try to think hard to what extent one can have a detailed account of behavior or cognition, which also involves a lot of auxiliary assumptions that maybe people generally don't like doing this, because they need to also commit to smaller ideas and smaller assumptions that they are not that comfortable with. But the issue is that without that, theories are very vague, and then we don't really know if they are right or not. There was, or there still is, a big crisis, a confidence crisis in psychology, for example. And it extends to other fields. It actually started from biology or from medicine, from this paper, I don't remember the author. Okay, but in any case, the issue is that there were claims that the problem was statistics, then smaller data sets. And then if we have better statistics, bigger data sets, then we will be able to replicate our findings. But it's not always the case, and it's also not that clear what we are doing collecting findings if we don't have an overall theory that can glue all these findings together and give us a complete image. And the idea of computational models is to give a more complete image of what's going on, that can explain several findings at the same time, that can explain entire distribution of observations and not just two conditions.
Okay. So I was thinking about economics, where people, and I don't know if this is true because I'm not an economist, I know a couple, but it's often said that economists are really good at explaining why something happened, but very bad at predicting what will happen. So basically they can apply their models backwards, but not really forward. And that could be because, the model is not complex enough that they use, or it does not take into account relevant factors. And of course, economics is an incredibly complex system that encompasses the whole world. So is the idea here that you create a model, you can test it out, and then you refine it, you refine the computations? Because I can imagine that if you look at a complex system, there are so many small factors, and you allude to that already, that your first computational model encompasses only a few of these factors and then will make fairly bad predictions.
Yeah, so I think there are several things we will never get to a place where a computational model makes all the predictions
that depends on the application, of course.
Yeah, at least in this type of models that we are talking about human beings doing stuff or animals, sure. And it's if you manage to make a model that doesn't that has perfect predictions, the model will be so complicated that then there is no chance to understanding it. And so the idea is to have an abstraction and capture some patterns that we deem as important. And so it's not that problematic that it can't capture everything. But given said that, one thing that's interesting is that you can create a model thinking about some phenomenon, then you feed it to that data, you get a good fit to the data, and then you decide to use the same model to generate new predictions about things that you don't have. So you simulate data based on conditions that are outside of your experiment. And then you can go and collect more data and see if that prediction of the model coincides with the real world. So you have that possibility. The idea is to have models that can generalize well, but they will need to generalize well to areas that we care about and not to absolutely everything. There is no way that we will succeed doing that, at least in cognitive science.
Okay, so okay, you related now to cognitive science, because I'm thinking I see different kinds of modeling. So we have, and that is the most common today. That is the big neural networks which are used as a model, and you feed them with enormous amounts of data, and then basically they form a model of that data. And these models tend to work really well, especially if lots and lots and lots and lots of data. Then they tend to perform well, though you don't know how long they will perform well, and because that might change over time. And then you have the statistical models, which just also get data but extract features from them, and then you already have a computational model, I think, if you use statistics, right? Because
you also have a computational model if you do deep neural network. The issue is if this computational model is explaining anything, and if this explanation is grounded in a theory. And in both cases, in most situations, kind of not really, because we know that behavior is not determined by a linear regression. And also we know that in many cases, these deep neural networks are much more complex and they need much more data than human beings. So even if large language models do a very good job with language, we know that they need an insane amount of data, and kids manage to learn and produce language with much less. So they are models and they are computational, but they are not grounded in theory, and they are not really cognitive. And the idea here is more to is to create cognitive models that are reflecting something that we know about behavior or cognition. And then I think that these are two extremes. One, the statistical model is too simplified. It's really easy to interpret and it's really easy to understand, but no way that we know already that people don't behave like that. And the other one is way too complex to understand, requires much more data, and it's really hard to see what's going on there. And computational models are in the middle.
Okay, so and can I ask something then about how the technology that you use to build these models and what they look like, and how complex are you talking? Can you give maybe for your cockatoo example or for the language example? So how complex is such a model then?
So there are a lot of types of model depending on what are the goals,
sure.
The level of abstraction that one wants to work with, and there are people that focus on that want to explain everything in the sense of like the entire behavior, and there are architectures like ACTAR and SOAR, and some people in the workshop that we had, there were people using that, for example, for negotiation. You can have two agents that negotiate, and you have the entire process there in those cognitive architectures. In my work, I tend to use models that are built in a Bayesian framework, not meaning that the mind is Bayesian, but meaning that you have uncertainty over the observations, uncertainty over the predictions, and then you have a model that's basically a series of equations, of formula that determine how long people will stay reading in one word, when they will move to the next word, how long a saccade will be. In the cockatoos example, I think that people use reinforcement learning, which basically is a series of equations that show how people behave when there is a reward or a punishment, and there is uncertainty over the environment, and it's basically a choice that's determined by a series of equations. So I think that in all these cases, you have equations that need to be implemented in some program. Could be Python, could be R. In the case of these cognitive architectures, you have like old school languages like Lisp. And then the goal might be to simulate data as a proof of concept. And then they will generate data that looks like the real data. And then you can compare if you are capturing the patterns that you care about, or you can fit it to the data that you already have and see to what extent, data point by data point, you have kind of a correlation between the data the model is producing and the real data. And it depends, again, and then you need to focus on some patterns that you care about, because as I said, this model, the predictions are never going to be perfect.
No, it reminds me a lot about my own major topic, which I love to talk about, is gaming. And in games, you often have, a game is always built on an engine, but the engine, in general, is developed by people. So they code the engine. It's not that they say, okay, create the engine by just giving us lots of data and we train on that. Although nowadays some of these simulation-like games do that. But most of them, they build the engine because they want to have certain effects. And often the effect that they want is to have something realistic happen. Like, okay, this game is about civilizations and they can have a war. When will war arise? And you can have the diplomatic inputs, and you can have military inputs, and you can have economic inputs, and these are all put in big equations basically, and they then determine, okay, now this country is going to declare war on that country. And since they want it to feel realistic to the player, that the player say, yeah, I expected that, they want it to imitate reality. Is this close to what you're talking about?
Yes. It's a series of equations that also they always have some uncertainty embedded in them, so that it's always probabilistic. The most interesting models, there are models that are deterministic, but the most interesting models, they're always probabilistic. And they look more or less like that. Then you have also models that are more connectionist, where you always have equations, but the idea is more to see to what extent some structure will give rise to the phenomena that we see, rather than what are the exact equations that lead to the behavior. But in these equations is where this kind of the science happens, where you implement the theory and you try to explain if something, to what extent people behave different when there is a reward or a punishment, or to what extent people will stay longer reading a word when they understand it or not. So these equations will determine the time it takes to read a word, or the choice that people are going to make, also including some randomness, because there is a lot of randomness in all these processes.
Yeah, I'm now thinking that maybe what game developers could do is, and maybe some of them do this, and you have the equations, also have a reinforcement learning mechanism on top of that, then let players respond to, okay, this didn't feel good. And then with reinforcement learning, make that the equations get more balanced so that they reflect reality better.
Yeah. I know I'm also teaching Bayesian methods in here, and then I teach reinforcement learning, and mostly students know it from the perspective of computer science, when you want to have the optimal behavior, but people are not optimal. And then if you fit a reinforcement learning model to people, what you get is how people behave, not the optimal behavior. And so an idea of all these models is also to capture the type of errors that people make, decisions that are not optimal, misunderstanding in reading comprehension, and not the idea is not to have an efficient system, but a system that reflects what people do, and ideally it reflects what people do because of the same reasons that people do it.
Okay. So if I summarize that, so the goal of the computational modeling of complex behavior is to capture human behavior in equations in such a way that you gain an understanding of that behavior.
Yes, but I would add the layer of computation because it's important. Because even when you have equations, sometimes you still have things that are a bit underspecified. And the moment you need to put it in a computer and you code it, it needs to run. And when it needs to run, you realize there are things that were left unsaid, that the equations were very elegant, but they were missing some crucial information. And then you need to get into the nitty-gritty details and really make it run. And then sometimes happens that these assumptions that one needs to add are arbitrary and you don't care about them, and then adds a new layer of complexity and you have different versions of the same model that follow the same basic equations, but smaller different assumptions. But you can also learn from these kind of ad hoc assumptions and see, and they can get later be incorporated into the model because you realize that they're fundamental and a lot depend on these smaller assumptions that were not your main equation, for example.
Okay, well, it feels a little bit to me that in the past already people, so this is not something completely new, right?
No, it's not. I think there are computational models since the 40s, and right. Alan Newell's idea was about building a cognitive architecture, was SOAR, and the idea was to how the human mind exists in the physical world. So these ideas have been forever, but the difference is that mostly people cared about it's already very complicated and they focus on very, very simplified tasks, and people still do that and it's still useful. And then it's not that clear how one moves from a very simplified task to one which is more complex, because the world is not modular. And then it's not that once I understand the small problem, I can extrapolate it to the larger one. You have, whenever you face a complex behavior, you have the problem of interactions with all sorts of components. And then it's not straightforward. And I think in the past, the focus was mostly on very simplified behaviors. And in part, one of the reasons was computational power. Some of these people did these computational models kind of by hand or with very old systems. And then I use Bayesian methods, which took days to run, and still they can take days to run if the model is complex enough. But the computational power increased by a lot. And so now we can have models that are more complex, and also we can tackle more complex behavior. But one of the issues is that I think that still people that are mostly focused on computational modeling, they are still working on very simplified tasks, because you can always continue and make them better and improve the models. And then you have people who work on complex behavior, complex phenomena, and they mostly don't use computational models. They haven't really learned that. And I think it's kind of hard to move from your niche where everyone is doing a comparison between conditions with ANOVA or with very simple statistical models, and then you don't even know how to think about your problem in a computational way.
Yeah, I can imagine that partly is because if you have a complex behavior, then the data-driven models tend to work so well that people are satisfied with what they do for them, rather than getting to that point of actually the understanding. Because if the model should work, then as long as it works, it's okay. Well, of course, understanding ensures that it may still be working in a year's time.
Yes, and sometimes also the goal is understanding. And then if you have a lot of, or sometimes you have also complex behavior with not that much data, which is also another problem. But even if you have a lot of data, you can have a very nice deep learning model that can make good predictions. But if the goal was to understand why that was happening, it's not necessarily that you'll get anything closer to your goal.
Yeah. So you organized a workshop on this with a couple of colleagues.
Yeah.
Which you wrote a paper on. I saw the paper. So one thing that I think that there were some lessons in the paper. So if you want to do this, how should you approach this? So it might be a good thing to bring that up here as well. I didn't think the steps were that weird or anything, but it might be good to lay them out. Could you do that from the top of your head?
From the top of my head, I will try. But but I think that there are things that are
or maybe what are the most important things in these steps?
I think that one important thing that was kind of surprising is that one needs to work hard also on formalizing the problem, because when it's a complex behavior, it's not that clear what should be the focus. If you want to understand something, you also need to understand what is the data, because it's not that the data. I mean, when we have already our data frame and everything is pre-processed, it is clear what counts as data, but it's not that data is over there in the world. You also need some type of theory to understand or to get what is interesting about this phenomenon and what should I record in order to model. And so that is not that trivial. And also from my own area, so I work in language, but in psycholinguistics, we mostly focus on reading times because it should be informative about the cognitive processes involved in reading. But if you look at people from NLP or people from education, they care much more about comprehension. And many times in my field, we kind of gloss over about what people understood from the sentence, and we focus on how long it took to read the sentence. And if it took longer, then we assume it was harder to understand. And so what is data also looking at the same language comprehension or language or processing difficulty or comprehension difficulty? What is data depends also on your field. And one of the things that we learned there that it was very useful and very handy to have a team, because then you have a discussion about what counts as data, what really should be the focus of what we are doing. If we want to understand how people read, should we focus on reading times? Should we focus on eye movements? Should we focus on comprehension of regular sentences? Should we focus on standardized tests? And all these things, if you have a group that's kind of multidisciplinary, then you have the opportunity to discuss this, because otherwise, when you always work with the same people that are already working on your domain, I think that the discussions can go very deep, but they are not very broad. We are always talking about the same thing and going deeper into that. So that was one of the things that was very interesting about the workshop, that you need to define, it's not that trivial to define the problem, and then the problem that you define and the data that you define and that you think is important for the problem depends also on the team. The people that you work with are going to determine a lot of things, and even the modeling framework, because you're not going to do reinforcement learning if no one in your team knows anything about reinforcement learning, right? And then the type of model and there are so many different models and so many ways to tackle a problem. And depending on the model, you are going to also focus on a different level of abstraction. Either if you are all you know are neuroscientists, then you are going to focus on neurons and less on behavior. And you might gloss over some important things that go beyond the neuron. So depending on who you work with, what are the problems that you're going to focus on, what is the data you're going to focus on, the type of models that you are going to work. And that was one of I think that was very interesting.
Yeah, one thing that struck me is that you specifically mentioned that you have to work in teams, but you now already explained why.
I mean, you don't have to, but I think it will be much richer if you work in teams. And then,
of course, it's a team of all kinds of the same people, then it doesn't work anymore.
Yes, it needs to be a team. It needs to be diverse enough, and then it will also allow you to work on. If your expertise is more computational, then you will hear about the actual problems that people that are more on that have the domain expertise are worrying about, that you might even not think about them because you never focused on that. And then people who are more on that have a domain expertise, they always discuss this phenomena among other people with the same domain expertise, and they are always talking about the same thing. And then they have the conditions that they deem important, and then they want to predict that if you do this, then you have a change, and that's it. But they don't think about the entire distribution of observations and what else is happening and what other predictions a model is implying. And then if you have a computational modeler in the group, this person will force you to think in a more computational way and to be more precise. And already having people from different sub areas at least will force you in being more precise.
Okay, you already mentioned conflicts between computational modeling and data-driven modeling, which seems to lean over to data-driven modeling nowadays. So can you say something about the future of computational modeling? Will it survive?
The kind of theory-driven computational modeling?
Yeah.
I think so, but I think that it's kind of complementary. The focus is very different.
Yeah.
The idea is understanding, and we have scientists all the time building their verbal theories, having intuitions about how the world works. But then I think that the place of this type of cognitive models or cognitive computational models is to force these people into be precise and to have very concrete predictions that can be measured. And I think it's a bit different from and then if we can have good predictions, all the better. But it's not the main focus to have perfect predictions. You can also have predictions that are less dependent on data, that can work in situations where you have less data. Most of the models that I'm aware of that relate to epidemiology, they are mostly based on theory, and they are not data-driven, because they have a lot of theory, and also because they want to have counterfactuals. If they have a theory that can capture different patterns in the world, and even if those things don't happen, you can model what would happen if you would change that. And a data-driven model is bounded by the data it has, cannot learn about the data it doesn't, and it will only generalize based on the data it has. It doesn't have priors or prior information or a structure that goes beyond the data.
Yeah.
And a computational model doesn't matter if it's Bayesian in the sense of Bayesian statistics, but can generate predictions a priori. You can, without collecting any data at all, you can already generate predictions of what you might get. And with a data-driven model, that's undoable.
Yeah,
so
sure.
you need a lot of data to even make it start.
Yeah, but I was actually thinking more that, and that's something that I personally believe. So you have these data-driven models, and they get very big and very complex, and they still make mistakes. And it's very hard often to find out why are they making mistakes or get these mistakes out. And a collaboration between different kinds of models, where you have the theory-driven models, which can actually criticize what is coming out of the data-driven system. I could imagine that makes the whole AI work better.
Yeah, yes. And there are also hybrid models where you have components that are data-driven, where you have no theory, it's not important how it works, and you want it to make it work, and you have enough data. And you have other components of the model that are completely explainable or rule-based and behave in a very specific way, because you have a lot of prior information there and theories about how they will work. And there is work on that also.
Okay. So, anything more that you want to add to this?
No, I don't think so.
I think we covered it reasonably well. Can you say maybe to end with something about your own research in this area at the moment?
Sure.
What are you working on right now?
So I'm always working in kind of a bit on methods and modeling in general, and a bit of language. So on the topic of models, I'm working on how we can compare models, because it's also not that trivial once you implement a theory and you transform it into a computational model, and you have different theories with different models. Given all what I said about these auxiliary assumptions, how we can compare them, and what model comparison really tells us about the model. So I'm doing simulations, looking at different type of models and what is the output of the model comparison. So that's on, and I also always, and at the same time, I also work on language. And one of the things I care about is about the link between cognition and time, how people can read at different speeds and can decide how fast or how slow they read, and at the same time they are affected by the difficulty of the text, words that are more unpredictable, take longer to read, but they are also at the same time modulating their own speed depending on their goals. So I'm kind of always working these two domains simultaneously.
Okay. So maybe to end up the whole thing, the paper that you have about the workshop, I thought it was a really readable paper. Lots of authors, but your first author, Nicenboim et al. What's the title of the paper?
Yeah, so it's called It Takes a Village to Model Complex Behavior, a Community-Based Approach. And it's me and other participants of the workshop. This paper is still under review, but the preprint is available, so you can take a look at it.
Okay, well, thank you. Then I think that's a nice ending of this conversation. Thank you very much.
Thank you.